Okay, let's get started. Got lots to say today. So, just on the administrative side of things, just a quick note that I really do appreciate all the feedback you guys have been giving on the last questions of the survey questions of the problem sets. It's super useful. So it's not so. Know that I'm reading and internalizing all of it. Know that it's impossible to address all of it. Like some people want me to go faster, some people want me to go slower, some people want more examples in MATLAB, some people never want MATLAB to be uttered again. And actually every one of those perspectives is extremely helpful to me. So very much, even if you have a very extreme view, I mean that's maybe some of the most interesting to read. But know that I'm trying, and we're going to do as much of it as we can. So there's a couple specific things I can address. Lecture notes have been coming out slow. I'm trying as hard as I can. But as a temporary stopgap solution, so I make these sort of chicken scratch notes for all my lectures. We're going to just post these immediately. And you can look at my dog might have sat on them. There's no guarantees. You'll see me make one mistake and scratch it out. Anyways, but they exist. They're complete, and they'll be up there now. Are they already up there? And then they'll be replaced by the proper ones as soon as I push the proper ones, which I'll do very quickly. Another quick point is that a few people have started asking about the final projects in the class, which is awesome. I think you should be watching the material as it goes by, see what captures your interest, watching the systems that we've talked about going by, and think about what's capturing your interest, and if you are identifying something you want to work on in the final project. You don't have to do that yet. There's going to be a problem set, I think 2 weeks from now, where we specifically ask you to come up with a project idea, and we'll start giving you some specific ideas. So there is a timeline that will start that hasn't started yet about the final projects. But if you're also thinking about how it affects your own research, all these things. But it's great to be thinking about it now. No pressure to be thinking about it yet. We'll do that soon. Just in case I forget to say it in the middle, so we're going to be using a new set of tools, of optimization tools for the materials we're covering today that you'll use on your problem set. And there's instructions in the problem set to help you with this deal. But there's a one extra solver that you'll need to install to use along with the MATLAB solvers. MATLAB's going to call a solver that can handle the types of problems we generate, the convex optimization problems we generate based on the material today. So you get your pick. You can install, if you love open source, then you can install Sadoomi, and it's free to the world and everything, but it's a little slow. And if you want to, if you don't mind installing the commercial solver and using the free academic license, it'll be faster and numerically a little better. So you have a moral decision to make. I installed MOSEC personally, which is the commercial one. Okay. So last time I tried to give you the background we needed to talk today about one of the topics that I'm actually most excited about that we pursue very actively in the research group right now, which is using optimization to do the Lyapunov analysis that we talked about last time. And I hope to convince you, partly today, but over the next few lectures too, that it's about more than producing proofs that a system is stable, but it'll actually help you in the control design process. So today is about Lyapunov analysis using sums of squares optimization. And so it's a bit of a tall order here to tell you all the pieces that we need to make you understand this story completely. So I'm going to do my best to give you the background only to the extent necessary to give you to understand the big idea here today. So we need to know a little bit more about optimization first. So we've seen optimization a few times in the class. It'll be a constant theme. A few examples that we've seen already, just to make sure it's all tying together. When we talked about the dynamic programming discrete update, we wrote down equations that said for every S, I'd like to make some update, which is minimizing over A, right? GSA. The equation's not so. This is just to jog your memory here of SA, where this was the state transitions. This was my cost to go, right? But in the middle, we started using the language of optimization, right? We used this minimization in the middle, and in the discrete case, that meant literally you could write an algorithm that tries every A and take the minimum value. Right, so that was sort of easy to program. Right, I try every possible A, because this was only looking over A's in some discrete set of transitions in my graph, and I plug it into this equation, I get a value out. Whichever one is the smallest value I'm going to keep, and that's the output of my minimization. That's sort of trivial, discrete optimization. You know, we've seen a couple examples in a continuous domain where we used the same language, right? We said min over u, and in the special case where we had some quadratic cost plus some f2u, if we had something that was quadratic only in u plus some other stuff, then in that case we said, okay, we can solve this minimization problem in closed form, because this thing, since I knew r was positive, then I know this thing is just going to look like some sort of quadratic bowl wherever it is. So if I look at different values of u, I know that it's going to be some simple thing like this. So I could actually find the minimum by looking at the place where the gradient with respect to u was 0 and finding that point. That was another instance another extreme where this was a continuous optimization. But we were able to solve it in closed form by just making a gradient argument, right? Now today we're gonna broach sort of the more complex forms of this optimization. So this already gets more complicated if I were to put some sort of constraints on u. Let's say if I added some bounds on u or other things, then this simple analytical solution doesn't work anymore, right? In general. Right, so the general sort of nonlinear optimization is hard. It's a hard problem. So, right, if I were to, in general, use the language, I'm going to minimize over some decision variables alpha, some objective. Let me write that as just some big function of alpha. Right? In general, if I don't have knowledge of what f is, that could be a really hard problem. If I plot alpha, I could have some complicated function f of alpha, and there might be not much I can do, certainly in closed form or even with a computer, to find sort of the global minima of this without sort of brute force searching. It might be very, very hard. So if I write this down in general, it could be hard. I mean, our goal would be to find some alpha star, but it might be that we find some local solution, which I didn't give myself a very obvious local minima here, but it might be that I get stuck with something here. If I'm just trying to look at gradients or something like this, I might get a very bad solution. It's hard to solve this problem in general. Okay, and the full-blown nonlinear optimization also allows you to encode extra constraints on alpha. I could say subject to some list of inequality constraints, G, that can be a vector G, right? Just so you have the language, this is a scalar objective function, right? This is my objective. These are my constraints. And these are my decision variables, right? Okay, so in general, optimization is hard. All right, so today we're going to talk about something that's maybe halfway between this general nonlinear optimization and the closed form solution. It's It's a problem that's hard enough that I have to ask the computer to solve it for me and just settle for a numerical solution instead of an analytical solution. But it's actually much easier than the full-blown nonlinear optimization problem, in the sense that there's a class of problems where if I ask the computer, I'm confident that it can efficiently find the global solution, right? So you can imagine that if f took a particular form, if f was some sort of easier function, in fact it's going to be a convex function, then I'm going to be able to rely on my computer to find the best solution efficiently. And similarly, if these constraints form a convex set, then I'm going to be in the world of convex optimization instead of nonlinear optimization. And it'll be surprising, it's been surprising to me how many problems can be formulated as convex optimization problems. And they have very efficient solvers available, which you'll download, either free or commercial. And they're going to be able to solve these problems for us almost to the extent where we could think of it as it being a closed form solution. Okay? So how many people know convex optimization? Feel like they've seen that before? Okay, that's about what I expected. That's good. All right, so let's just tell you a little bit specifically what I mean by convex optimization. So now this is a rich topic. You could take a whole semester course on it. I feel like I say this every lecture. It's really annoying. So it's a rich topic. You can take a whole course on it. I'm going to spend 5 minutes on it here, but I think you're going to have enough to be able to be extremely effective with the tools. Okay? Oh, I'm sorry. Yeah.
So when you're performing this, how do you know your value functions on the right hand side? So you have to know something about the convexity of that a priori to actually use this method.
So I wanted to put that in context with the value function stuff we did before. You're going to see immediate application today with the Lyapunov instead of the value function, and it'll be crystal clear in a few minutes. Yeah. So how would you use that in the value iteration loop? We have an answer for that too, but it's a slightly harder story. Okay. So what does it mean to be a convex function? I think you know intuitively what it means, right? So a function is convex in its parameters if it's shaped up, if it's sort of pointing upwards like that, right? So what's the technical definition, right? So if I take any 2 points, let's call it alpha 1 and alpha 2, and I look at the function evaluated at those 2 points, then I should be able to draw a straight line between them that is everywhere above or equal to the function. That's how we're going to define a convex function. Okay. I can write that mathematically very simply. This line segment here is defined as a affine combination of those 2 points. So if I make a number beta that goes from 0 to 1, and when beta is 0, I'm over here, and beta is 1, I'm over here, I could write that as beta alpha 1 plus 1 minus beta, let's say alpha 2. That would walk the line between here and here, right? That would parameterize this line segment down here, right? And what I care about, should use my colors. What I care about is what's the function over that interval. Okay, so I would like that some linear combination of these points, which is going to be, let's say, beta f of alpha 1 plus 1 minus beta of f of alpha 2. Right? That's my combination of this. That had better be greater than or equal to the function evaluated at the point in between. So Okay, that's just saying exactly what I said in pictures, that this line, the combination, and this is always for that, yeah, this line is everywhere above the function. Very simple definition, simple test. So our objectives in convex optimization should be a convex function. The other thing we need to understand is our constraints have to be a convex set. Okay, so intuitively what a convex set is if I have some region of possible parameters, let's say it's in alpha 1 and alpha 2, right? And I say any of these are okay. Then what that should mean, the definition of a convex set is if I pick any 2 points inside that set, then the line connecting them should also be inside that set. The line segment connecting them. Yeah. So exactly analogous, right? So if alpha 1 and alpha 2 are in some set, call it G, I guess, then beta times alpha 1 is 1 minus beta. 2 had better be in G. Okay, so my objective, you can imagine that if my objective is like this, it should be easy to find the minima. What the function being convex implies basically that there are no spurious local minima. There's no place to get stuck if I'm doing optimization. Yeah? And the set being convex is important for that too, because you could imagine, let's give an example of a not a convex set, right? If I had some set like this, right? And this not convex, right? Then you can imagine getting a solver getting stuck if I've got some, even if I've got a smooth objective function and I'm trying to get down, then maybe I have to, maybe the minimum is over here, but I'm stuck here thinking I can't go any farther, if that makes sense. If I were to be looking at the objective along this line, it might look, even if the objective is smooth, there might be a gap in what I'm allowed that prevents me from ever looking and finding my path down to the real minima. So you need both in order to have an easy optimization problem. Does that make sense? Okay, so I'm going to spend more time thinking about the sets that can be convex for today. Okay, so let's think of some simple examples of a convex set. And again, this is actually already posted. It's something I've been wanting to say. Okay, so up to the resolution of my scanner and my calligraphy skills. Okay, so one of the most famous convex sets is a half plane. Okay, so if I have some vector like this, if I just have a line, the equation of a line, and I'm less than or equal to some constant, then this is really, if in alpha 1, alpha 2, that's just a line. And the inequality means that it's called a half-plane constraint, right? Linear constraint. And if I have multiple linear constraints, then the intersection of many linear constraints is going to be a convex set, right? So if I were to have another linear constraint like this, then the union might not be convex, right? That would be bad. But the intersection will form a convex set. And so in general, I can just list if I have a list of constraints, if I list many of these together, I can write AX less than or equal to B as a set of linear constraints. It's the intersection. If all of those have to be true, that's the intersection of half-plane constraints. Okay, and there's a lot of other very important examples, but the one we need today is sort of awesome. Okay, so it turns out that the positive semi-definite matrices, if you look at the, if you write down a positive semi-definite matrix, which I'll write down as PSD, right? And if you look at this parameterized by its elements, okay, it turns out that the set of all positive semi-definite matrices forms a convex set. Okay? Okay, so first let's just make sure we understand that that is true. So what defines a positive semi-definite matrix? The definition is that it's a matrix is positive semi-definite if for all x, x transpose px is greater than or equal to 0. Right? And then the question is, if I have two positive semi-definite matrices, can I convince you easily that the affine combination of two of those is also positive semi-definite? And it's easy. That was actually an easy thing to see. So then if I have P1, P2, both positive semi-definite, then I'm asking about, can I say something about beta P1 plus 1 minus beta P2, right? And so the question is, for all x, x transpose of this guy, this is for beta. Right? So it turns out that, by linearity, I can pull this inside. This thing is the same as x transpose beta P1 of x plus x transpose 1 minus beta P2 of x. And by those are just scalars, so I can pull them outside. Beta x transpose P1 of x plus 1 minus beta x transpose P2 of x. And if P1 of x, if this is always greater than 0, and this is always greater than 0, and this are always greater than 0, then I can safely say that that's always greater than 0. Okay? So the set of all PSD matrices forms a convex set. That's totally abstract when you first say it. Okay? It turns out to be extremely useful. So what does it mean? It means that I can write an optimization down where my decision variables might be the coefficients of some matrix. And if I put down as a constraint that matrix has to be positive semi-definite, then that's still, as long as my objective is also convex, that's a convex constraint. So in practice, what it means is I'm going to be able to ask a solver to search over the positive semi-definite matrices, and that's going to work. That's going to be something that the solver is going to be able to do very effectively for me. Okay? You should have in your head that it's one of these easy minimization problems that the solver can handle very well. Okay? And the algebra should convince you, but it's hard to get your head around it. It turns out, yeah, it's called the positive semi-definite cone. The particular geometry of this is a is a cone structure because I could always, if I have a positive semi-definite matrix, I can multiply it by any scalar positive, and I still have a positive semi-definite matrix. So geometrically, it looks sort of like a cone, but it turns out to be an easy set, a relatively easy set to search over. Okay, and that's going to have lots and lots of applications for us. And I don't want to keep you waiting. Here's the first example of how that works for Lyapunov analysis. Okay, so so how can I do? Well, let me just say the optimization over PSD matrices is efficient. Yes?
You say that we can easily optimize over PSD matrices. What are we actually trying to do there? Aren't they specifying our constraints?
So I'm going to give you a perfect example in just a second. It's a good example, I think. But and ask again if that doesn't clear it up. Yeah. So basically, I want to find. So I don't know what positive semi-definite matrix I want. Okay, but I'm telling you, if I can describe with some objective function, and maybe a multitude of constraints about the parameters, it could find a positive semi-definite matrix that I could find a solution which is positive semi-definite and satisfies some other constraints too. For instance, it could be a Lyapunov function for my system. If I'm going to search for a Lyapunov function, and that means I have to find some positive semi-definite matrix P, and I don't know exactly which one's going to prove this system, but I can search over the positive semi-definite matrices with these tools. Okay, it's efficient. It's got a name. It's called semi-definite programming. SDP. Okay, so for instance, we talked about the Lyapunov conditions for linear systems. Right? We said if there's some stable system, x dot equals ax, then I should be able to find some matrix P that is a Lyapunov function for that system. Right? And what I'm saying, and the way that I can prove it's a Lyapunov function for the system is I have to check the derivative, right? I have to check that P's got to be positive, and the derivative, which we said works out to be this has to be everywhere less than equal to 0, right? So if I can write down an SDP, semi-definite program, and even if I don't even have an objective, right? If I'm going through life just asking for feasibility here, I can ask these solvers to say, find me some parameters P, some matrix P, such that P is positive semi-definite, and PA plus A transpose P is negative semi-definite. And the solver will kick out a solution if it exists. That's the big difference about convex optimization versus general optimization is I can ask the solver to give me this. it'll either say, here's the optimal value, or it does not exist, or there's no feasible solution in this set. Right? So if I put these two constraints together, it's not that every positive semi-definite matrix is going to satisfy that. There's only some positive semi-definite matrices that will solve both of these constraints simultaneously, but I can search over them. Okay? It's important that this matrix here is linear in the parameters still. There's affine in the parameters that they only enter in a certain way. But the theme here is that I can put down constraints on the definiteness of my matrix. Yeah?
There are only multiple solutions, so which P do we pick?
Yeah. So we could put down an objective. We could say, find the smallest one, or something that might be bad. Maybe find the one who's closest to, whose trace equals 1 would be a natural thing. Something to just give it an objective in life. If you don't give it an objective, these things are typically solved with a class of optimization techniques called interior point methods. And they'll try to find sort of something kind of in the middle of your convex set. And so it can be okay to not have an objective. But you're right, there's multiple solutions, right? And you'll see in more specific examples, sometimes there's a very natural objective to put on top. And sometimes you really would accept just about anything that satisfies. Okay, do you feel empowered? Yeah.
Which need P to be positive definite instead of positive semi-definite.
Good. Well, it turns out that so that's a really good question. I tried to slip that past you here. You can ask for definiteness, or rather, you can inspect your solution, right? So it might be that if I put down an objective that encouraged it to be more positive. But certainly, when I get something out, I can just check the eigenvalues of P and see if it is positive definite, if I require strict positive definite. Yeah, and you can often encourage that. So if I said, for instance, that P, let's say I want P minus, 1e to the negative fifth times I. It's got to be greater than or equal to 0. That would do it. So there's some, but even if I do this, there's a little bit of care required because I'm still going to get this only to some numerical precision, and so at some point, if you're asking it to be a strict proof, there's more details to address. Right on. Yes.
What if P is very ill-conditioned? It's an ill-conditioned matrix, and some of the eigenvalues are very large.
It's a great question. So. It depends if you use the commercial solver or the free solver, is one answer. But there's a lot of different solvers out there for convex optimization problems. So you might have heard of linear programming. You heard about quadratic programming when Scott came and talked. The commercial solvers for LP and QP are extremely sophisticated. If you give me an LP and a QP that's numerically badly conditioned, it will fix it up, solve a good problem, and give you an answer. And you don't have to worry about it. SDP is a newer set of problems and a harder set of problems. The solvers don't do as good of a job. So you can set up a problem, and it'll come back and say numerical error because of badly conditioned numbers. And we face that a lot. But almost always, if you look more carefully what you've asked for something silly, and you can do better. So, but that's a great question.
I have a question.
Yes?
Is it easy to decompose a convex set into finite convex sets?
No. So in general, it's NP complete to do that. So it's like a hard problem. It depends on the dimension of the set. I could point you to Robin in the back row who could tell you all about it. But it's not trivial. And even if you did, then you end up with a harder optimization problem. You might have to check all those sets individually, and that can be combinatorially bad. There are some solvers that will do that. You get into these mixed integer quadratic programming kind of solvers. So, but it's a harder class of problems. But I wanted you guys to yell at me about something, and no one's yelled at me. I mean, you've yelled at me about other things. But there's a reason you shouldn't feel empowered yet. which is because I told you you actually don't need to do this, right? I already told you how to solve. There's a solution to this that's known. It happens in the case of a stable linear system. I know how to find p by just solving a simple equation in MATLAB. Right? I said if you just set this equal to any positive definite. This was a detail I just said on the side, but if you were really paying attention, you would have say that if I just set this equal to any q greater than 0, and then solve that equation, then I would have. For the specific case of linear systems, that is actually sufficient. That would have worked. So we haven't actually done anything new here. We just called a solver instead of solving an equation. But I can make the problem harder and do something new. Okay, so let's do a slightly more complicated example. Right, so this works up to numerical precision. It's just not strictly needed. Here's a slightly harder example where it is needed. Okay, so robust analysis. Using the common Lyapunov function idea. Okay, so now I want to start this with the same premise almost, but this time I'd like A to be uncertain. Okay, bounded, I want to be able to put limits on what A can be. If A can be anything, then I've got no hope. But uncertain. Okay, so there's different ways to specify your uncertainty. One way that we're going to use here is, let me say that A is some combination, some affine combination of different matrices, AI. So I don't know, you can imagine if I have, you could think of it in the parameters of, I could be this system, I could be this system, could be this system. I don't really, this is just one way to specify an uncertainty set. All I'm going to tell you is that the real system is somewhere inside this, is some affine combination of these. It's somewhere inside this region, this polytope. Okay? So that you could say, for instance, if my quadrotor had unknown inertia, I might be able to specify it like this, right? By saying, here's the inertia with 0.9, here's the inertia of 0.1, and it's going to be somewhere in between the two. I want to write it this way just because that's going to make the demonstration very easy. Okay, so my claim is that it's going to be sufficient to say I'm going to find, search over P, some positive P. I could parameterize it so that it's symmetric easily. Okay. With the extra constraint that for all of these i's, individually, those systems are going downhill. So my claim is if I can find a single Lyapunov function, which proves that every one of these corners of my polytope here is stable, then I've proven that every system that's an affine combination of it is also stable. And you could convince yourself of that if you look at P dot of the original, V dot of my real system is going to be sum over I, beta I, P times this plus this thing sum over I beta I AI transpose P. Right? And I can pull these betas out. Right? So if these are all independently less than 0, and it's a affine combination, I should say, sorry, I forgot to write that beta is greater than or equal to 0 for the affine combinations, then this thing is certainly equal to 0, less than or equal to 0. Okay, so that's something new. That's something we couldn't do before, is find proof of robust stability for an uncertain A. There's no closed form solution for this, but there's a SDP solution for this. That's pretty cool. In fact, I can run it. So this code I'll give you just so you can think about it, but really what I want you to see is that it's simple. I guess that's the point, right? So I want you to be able to read this on your own, but right now I want you to believe me that it's very simple. So I'm going to make an optimization problem. So first I generated some random stable matrices. Okay, I did that by standard sort of I choose the eigen vectors at random. I make sure all the eigenvalues are negative. Okay, and then I'm going to ask my optimization to create a new positive semi-definite matrix P. So that's adding the constraint that P had better be positive semi-definite. Now it's by default it'll actually make a symmetric matrix for me too. And then I'm going to add extra constraints like this for I equals 1 to k. I'm just going to add this saying, okay, optimization. This had also better be positive semi-definite. Right, because I had been writing down that matrix was negative semi-definite. I just multiplied by -1 to get a positive semi-definite matrix. And then I'm going to optimize. So here I minimize the trace of P just to have an objective, and I'll display the results. It happens, instantaneously, and you can put a lot of matrices in. I pushed it down, which was may or may not have been a good thing to do, but I get a positive semi-definite matrix out. Okay, so really the point is that there are solvers that are really take these constraints in relatively high level with a relatively high level specification, and they're very fast and they just work. Okay. Now what's interesting is that might have not worked, right? This is only a sufficient condition. I could choose random, stable linear systems and not be able to find a commonly Lyapunov function. It could be that there is no commonly Lyapunov function that proves all of them are stable, because I know it is well known that the set of stable linear systems is not a convex set. So if I run it a few times, see how lucky I get. Oh, see, good. Failed, right? So for that randomly generated set of matrices, I couldn't find the solver. But it told me very quickly that's still a success, right? That says this problem was infeasible, and I told you very quickly. Okay? Good. So this is a different class of problems. It's a different beast. But this example, I think, is a very important one because it's connecting the Lyapunov analysis, which we talked about last time, very powerful. I showed a linear system example, with optimization. Right? I'm going to use the mysterious part last time was how do I find P? Right? You guys asked that. That was a fair question. How do I find P? You just pulled it out of thin air. Here's the answer. The solver is going to find it for me. Okay? That's a new answer. That's an answer that we didn't have. I don't know. I guess we've had it for a while now. If I say the same thing every year, then it starts getting, old. So now it's been around for a handful of years. But that's a cool thing to do. Okay. So that's a really key example, but it's only for linear systems. How do we do nonlinear systems? All right. There's something magical that happens in between here. I hope it won't be mysterious, but it was very surprising when I first heard about it that it's true. Okay, so we just said that the search over the positive semi-definite matrices is something you can do with convex optimization. That's cool. That's maybe initially surprising already. It turns out that we're going to be able to search over positive polynomials using the same tools. Okay, so if I have a polynomial function and I want to ask, is it positive everywhere? Is it always greater than or equal to 0 for all x? Shockingly, surprisingly, that's also something that we can do pretty darn well with semi-definite optimization. All right, so we're going to search over positive polynomials. And really, it's very surprising that there's this strong analogy between if I write some polynomial, which say parameterized by alpha, over some variables x, okay, which in the univariate, if x is a scalar, then it's just polynomials, the ones you know about here, right? And of course, if x is a vector, I can still write something out. I could write it as alpha 0, alpha 1, x1, alpha 2, x1, x2, and in some, that's not equality from there, that's just another example. Or, I could write some polynomial in multiple variables, of course, too. And the claim is, if I want to, for instance, minimize over the coefficients, alpha, some convex objective, and the solvers consume linear objectives. If I want to minimize some, some objective, let's say C transpose alpha. Can't believe I wrote down alpha transpose x. Subject to the idea that for all x, P of alpha x is greater than or equal to 0. That's going to turn out, this is just my weights. My objective. Okay, this turns out to be something I could do with semi-definite programming. Or really a layer that sits on top of semi-definite programming. We call it sums of squares optimization. There's a few superstars in the world of sums of squares optimization. One of them is on the faculty here, Pablo Carrillo, is upstairs. He basically found this connection between sums of squares polynomials and STP and systems theory for his PhD thesis. So if you guys haven't finished your PhD thesis yet, there's the bar right there. Yeah, pretty impressive thesis. So we reference the thesis as one of your background reading, if you like. Okay, so and there's actually the theory of this is beautiful. There's lots and lots of connections. It's not a superficial connection. There's lots of deep connections between what people know about polynomials, which lives in algebraic geometry, and what people know about optimization, Lots and lots of really nice connections. And there's a class, Pablo teaches a class on it too. Okay, so in fact, I can put down lots of potentially, multiple polynomial constraints. Right, so this is a big idea. We're going to use it now to try to think about. First, let me convince you that it's true, and then we'll use it to try to do Lyapunov analysis for nonlinear systems. Yeah? Or do you believe it's true? I think I have to say a little bit more to convince you, but let me try to say it efficiently. And just so you have the intuition, okay? So, all right, so how do I prove, if I have a polynomial like this, how do I prove that it's positive for all x? Right? So, well, the title sort of gives it away, but, I mean, so let's just think about it. So, is this positive for all real x? Yeah, that's positive, because that's positive, and that can only be positive, right? All right, I got a better example here. So what about 2 minus 4x plus 5x squared? Is that one positive for all x? That's not as clear.
You can write it as a sum of squares.
If I can write it as a sum of squares, right? So turns out I can. Turns out if I write it like that, then a little bit of algebra will show you those are the same. And now you believe that it's positive everywhere. Okay. So how do I factor this into that, if that's the goal? It turns out, I think really shockingly, that I can ask an STP solver to factor that for me. Okay? So here's the idea. So I'm gonna slide transition here about a real estate. Okay, how do I ask an STP solver to factor something like that? Okay, you think about like symbolic things, trying a bunch of different factorizations. It turns out if I were to write it like this. Okay, so I'm gonna say I want this to be some combination of basic building block monomials, very simple polynomials, if you will. Let's say I'll write down, I've got to have some combination of these. I'll make squared combinations of these. Okay, and then I'm going to put a matrix in between. Oops. 3, 1, 2, 2. And these would be, I'll constrain it to be symmetric. Two. Okay? So I'm going to say, find me a matrix A, which, guess what, is PSD. I'll call that matrix A. And I'm going to ask it to be positive semi-definite. And if I can find a positive semi-definite matrix A, which also makes this equation true, then I've actually found my factorization. And it has to be a positive sum of squares by virtue of this being A. Okay? So I have this, I have some free parameters here I'm trying to decide over. I have a constraint that the matrix that they form is positive semi-definite. And then I have some extra constraints which have to be true for this equality to hold, right? So I know that A11, when I put it through, had better equal 1. That's the only thing that can equal 1. And A21, it turns out, had better be equal to 0. And A22 plus 2, I'll just cheat now, 3,1 equals 2. There's just just to make that equality hold, there's some constraints on those elements. But they're all linear constraints. They're my half-plane constraints. Or these are actually equality constraints. So they're line constraints. All right? And I can now put this together and say, find some A that satisfies all these constraints and is positive definite. And if I can find that A, then I found my factorization of that polynomial. That's awesome. That connects this sort of very symbolic feeling factorization problem into a numerical problem. It happens to be a numerical problem I can just call the solver and get an answer to. Okay? There's some caveats, some asterisks, some important side notes. There's a lot known about the gap between positive polynomials and polynomials that have a sums of squares decomposition. There are actually positive polynomials that for all x are always greater than 0, which cannot be factored into a sum of squares. So that's a bummer, but that's okay. It turns out for us that's not gonna slow us down, because the basic idea is that there's so many Lyapunov functions that can prove stability of the same system that the fact that maybe I'm going to search over not every Lyapunov function, it's going to be okay. All right, but I have to sort of say that there's cases where it's known to be tight, but there is potentially a gap between the positive polynomials and the sums of squares polynomials. Okay, so that's the intuition of how you'd use an STP to factorize a matrix, and really the trick is listing these monomials out and then doing some linear combination, some combination of those monomials. So like the complexity is maybe in listing out the monomials. There's a lot known about what monomials you need based on the total order of this. So you don't have to guess them. The solvers will do that for you. Okay, but you could maybe think about this like, I don't know, if you're a machine learning person, think of it a little bit like the kernel trick, right? Or it's a little bit like our function approximator. The fact that we can do great things with linear function approximators, even though they've got nonlinear basis functions. In some sense, the richness is in the basis functions, and then simple combinations of them can do great things. Okay, so this means that we can do nonlinear Lyapunov analysis. Right, so let's say I have a polynomial dynamical system, right? If I'm willing to write V as some polynomial, let me write it like this, where M is my combination of monomials. Okay, so if I write a grab bag polynomial Lyapunov function, and I want to search for the Lyapunov function by searching over the coefficients of the Lyapunov function, then I'm going to be able to write down an optimization problem which says, find me some parameters alpha such that V is greater than 0 and V dot, which remember is partial V, partial X, which will be polynomial. The derivatives of the polynomial are still polynomial, times P of X is less than or equal to 0. Yeah? So I don't have to be mysterious or magical about it. I can just say, all right, solver, find me a Lyapunov function that matches all these conditions. And I'll put the caveats on it in a second here. And basically, if there's one that exists, the solver will tell me it exists. Or it'll give me the Lyapunov function. If it doesn't exist, it'll say it doesn't exist. Or it could potentially say numerical errors. Or it could say, blah. If you ask for too big of a system, right? If I try to do this just brute force on Atlas, for instance, it'll go off and try to allocate all the memory on your machine and your neighbor's machine, and then just never respond. That's the other failure mode. But for pretty decent sized problems, it'll tell me my Lyapunov function. Yes? That's pretty cool. Now this was for global analysis, so we have to do more if we want to do local analysis. But does that make sense? Yes?
So does this only work if P of X only has one root?
Nope.
So,
Nope. You can have, yeah, you could have, so you guys start getting into the subtlety of whether this is strictly negative definite or not. So if I have, so let's say something that has two fixed points, that would be the roots of P are the fixed points, right? Then of course I'm not going to be able to prove global stability of this, but I could still prove something that says with Lassalle's argument, right, that the sum of the invariant set which contains both of those fixed points is stable, right? If you ask for something to be strictly positive or strictly negative definite, then you'll fail on that, unless you can do things like tell it to ignore a point. And there's all kinds of variations of this. So the short answer is that's not a problem.
How general is it that all systems will be polynomial?
Good. I'm going to address that in the last few minutes. Yeah? Not all systems are polynomial. You can Taylor approximate any system. And in fact, that's only partially a cheeky answer. We actually do that a lot, right? So it's if it's smooth, if the nonlinear dynamics are smooth, non-polynomial, you could Taylor approximate it and do fairly well. And you could even put bounds on your errors of your Taylor approximation if you want. But I'll convince you by the end that actually robots are polynomial. Okay? So, or I hope to convince you. Okay, so this is for global stability analysis. The other big thing we did was region of attraction analysis with the Lyapunov functions, right? So how do I do region of attraction analysis with this kind of a tool, right? This is a challenge for you, right? So I'm telling you that for our current purposes, there is an oracle that you can ask. You can take your polynomial to this oracle and say, oracle, is this polynomial positive, greater than or equal to 0 for all x, right? And he or she will say yes or no. That's our abstraction for now. Okay, you can take the polynomial there, you'll get a yes or no answer. But now I want something that, if I want to prove that something's stable if I know it's not stable globally, right? I know the answer is going to be no if I just say, can you find me a Lyapunov function for the entire state space? The oracle will say no, right? So what if I say, okay, what about for this part of state space? Can I find a Lyapunov function for this part of state space? How do you rephrase your question to the oracle so that their question answering system will give you what you want? Yes?
Can you multiply your polynomial by a column that put it at 0 right in that slot?
You're almost right on. So what Audrey said is that basically if I have a polynomial and I know that it's, let's say, negative someplace, maybe if I just multiply that by 0 everywhere in the place that I don't care about, then my oracle will say yes. Okay, but the problem is multiplying by 0 and then non-zero somewhere, that's not something I can represent with polynomials. So the idea is very good, but so in order to ask the oracle, to be a valid question for the oracle, you have to ask it in terms of polynomials. Right? So how can I take my original question and sort of zero out the things I don't care about, but with a smooth function? Right? Do people get his idea? Was just zero out the things I don't care about, right? It's basically exactly that, but I'm just going to try to. I'm going to ask the oracle, find me a smooth function, right? I'm going to, give me a function which I can make positive. I'm going to give you some extra free variables that will make something positive where I don't care, but won't change my answer in the part I do care about. That's the idea, and it's a Lagrange multiplier kind of idea. So how do I do regional analysis? It's via, so different people call them different. I think it's most simple to call them Lagrange multipliers. It's also known as the S procedure. It's also known as positive Stellensatz. This is from the algebraic geometry view of the world. That's the problem is when you find these deep, beautiful connections between different fields, you get weird names for things, I guess. Positive, I think I wrote that right. I told Ani and Michael this is my biggest test for the lecture was if I could write that correctly. All right, so the idea is if I want to ask, is P of x greater than or equal to 0 for all x where let's say g of x, some other polynomial, is less than or equal to 0. All right, if I can define my region with another polynomial, then it's enough to ask, is for all x, is P of x plus lambda x g of x greater than 0 for some polynomial Lagrange multipliers. I'll show you a specific example of this. I'm going to make up some new polynomial lambda of x. Okay, and the idea, this thing is only ever positive. The thing I want you to understand is that when g of x is less than 0, then that means proving this is positive only got harder, right? Right? When g of x less than 0, it's only harder to prove. So it's a sufficient condition again. And then when g of x is greater than 0, then I can make it arbitrarily, even if P of x was negative, I can come back and add sufficient positivity to make this whole thing be positive. So it's almost exactly what Audrey said, where I'm going to just add in something else in the parts I don't care about to make the oracle say yes or no the right way. Yes?
This thing not handle non-polynomial constraints? Like, why not just specify your lambdas and your g of x as a constraint as opposed to?
Well, I thought I understood your question, but the second part threw me. So you're saying, so it is the case that we're magically relying on polynomials here.
Right, but you want to search over space where these polynomials are less than 0.
Yes.
Why not just specify that as a constraint and let the application deal with it, as opposed to specify it as a multiplier?
Okay, really good question. I think I understand. So, so this is not a constraint on the decision. X is not a decision variable. No. This is a subtle answer, I think, and I want to make sure we get it right. There's in the sums of squares problems. I'm going to flip back to the previous page here. Okay, there's two sets of variables flying around here. There's my decision variables, and I can put constraints on my decision variables. And then there's these indeterminates, okay, which are something that these things have to hold for all possible x. So I can't. So that's a separate thing. So I could put linear constraints on alpha, absolutely. But the only question I've learned how to ask so far is how do I ask for something for all x, for the indeterminates. That's what my oracle's capable of, which is a little screwy, but that's what we got. That's what we can map to the semi-definite programs. And it's with tricks like this that we can accomplish what you're hoping for. Okay, so let's do, does that make sense to people? Yeah? All right, let's. I mean, I think this is something that you kind of have to chew on, but it sort of makes sense that I'm going to draw a picture of it in a second. All right, so let's put it to work. So let's say I have x dot equals negative x plus x cubed. It really is my favorite example. This one here, right? It's so clear, okay? Right, so I want to, remember we said last time that I was able to prove stability with x squared, and it turned out that v dot, it gave me exactly the region of attraction I wanted. Let's ask sums of squares to do that for us, okay? So I'm gonna formulate this for you. I'm balancing how much time I have left here. So here's how to make it a little bit concrete. I want to find, I know what v dot is. It was 2x squared plus 2x to the fourth, right? So minus 2x squared plus 2x to the fourth, yeah? I'm going to make a new polynomial, which is going to be my Lagrange multiplier. Call it C0 plus C1x, C2x squared. Now, it stinks, but to write it in the algorithm, I have to pick the degree of this, and this one I can't tell you there's a good answer for necessarily. There's some heuristics, but you just have to guess how much you need in the polynomial, what degree you need here. If you fail, you can increase it, but you have to guess that one. Okay, and I'm going to ask that, I'm going to say find the coefficients C subject to this thing being negative semi-definite in the region I care about, which is equivalent to saying the part I care about is when v is less than 1, right? The true ROA, I know, happens to be whenever v is less than or equal to 1. So I'm going to say, can I prove that by finding some Lagrange multipliers which demonstrate that this thing is actually strictly less than or equal to 0 in that region? Okay. Okay, so let me step you through this a little bit here. So I'm going to say there's some symbolic variable, x, some variable that I want to be my indeterminate. Okay, I construct my program, I say that x is an indeterminate. That's something that, whatever I prove, I want to prove for all x. I define the dynamics in terms of that, and I define my Lyapunov candidate here in terms of that. Okay. And then I'm going to add in, I'm going to say I've got some decision variables here. They're free variables, C. I'm going to make my lambda, which is exactly what I wrote here. It's just C times some monomial vector x. Okay, and you're going to have this code, so, okay, but I'm going to add this constraint. Oh, I forgot to write here that I also have to say that lambda x greater than or equal to 0. Okay, so lambda has to be positive, and then my v dot plus lambda 1 minus v has got to be positive. Now, because there's this gap between negativity and strictly negative definite and negative definite, and positive negative semi-definite, I'm going to add in a little. I'm going to ask it to be not just negative, but I'm going to ask it to be smaller than some slack pair. I'm just going to add this in for numerics to have an objective to say, actually try to be really as negative as possible. And then I say minimize, make that as small as possible and display the results. And I'm going to plot a couple things for you when it runs. Okay, so here's my x cubed. This is v dot. You already know that that is negative only up between -1 and 1. It couldn't be more, right? How do I prove that? I find a Lagrange multiplier, this lambda, which is some positive function, which when I add it together, now this is v dot plus lambda 1 minus v. When I add it in together with this, it makes a function which is in fact negative everywhere. Okay? Now I'm gonna let you chew on that by putting it in the notes and everything. But this is, it turns something that is not negative everywhere. It goes off here, and it adds in something that kills these terms, so that I can use my oracle to prove stability. Okay. Hope that makes sense. There's tons of examples we could do from here. One of my favorite ones here is the van der Pol oscillator. Okay, so it turns out that you can even search for V. So that in that case, in the region of attraction case, I just tried to search for the Lagrange multipliers, but you can search for the coefficients of the Lyapunov function and the Lagrange multipliers at the same time. Okay? And we've packaged it all up for you. There's going to be problems that are going to force you to think about it, but we've also made it very easy in Drake to do it. There's just a method you just call, give me the region of attraction, and it'll do everything for you and spit out the region of attraction. And for pretty complicated systems, and does some things to make the numerics right. Okay, so the van der Pol oscillator is this cool system. This is actually the time-reversed van der Pol oscillator. The oscillator, by default, will just, it happens to be a well-studied system that has this stable periodic behavior in the phase. This is Q and Q dot, okay? All that matters for the purposes of this is that it happens to be a system that's polynomial, which is good, that has a known region of attraction. If I time reverse it, then this region here from numerical simulation, I know is the true region of attraction to the fixed point. I run my region of attraction sums of squares algorithm, and what I get is something that, whenever I get an answer, it's guaranteed to be sufficient, but it's not guaranteed to be tight. It's always, every decision is made to be conservative, so that if you get an answer, you can trust it, but you may not get the biggest answer. So what you get is an inner approximation here. This is now, it searched for a fourth order Lyapunov function, polynomial Lyapunov function, which is an inner approximation, but as big as possible inner approximation that proves stability to that point. And this is what you get. This is the true region of attraction. This is the estimated region of attraction. Okay? Extremely, extremely cool. Okay, yes?
Frequency expand the slab. What is the slab in the previous problem again?
So instead of asking for v dot to be just less than or equal to 0, I said I'd like v dot to be as negative as possible. The way I did that is I said v dot plus some slack variable times x squared is less than 0, and make that slack variable as negative or as positive as possible.
So we just randomly choose that function, like to make it a little bit.
Yeah, x squared is just some function that, because I know it's got to be 0 at the origin, and then try to find something that pushes it down, just to put a weight on it to give it an objective. Okay, so we're going to see this again in a couple different times throughout the course. There's lots of things to say about this. There's lots of different formulations. Some of them are beautiful and simple. Let me just say that rigid body dynamics are in fact polynomial, and I'll convince you of that next time. Okay. And the other thing I want you to understand is that the case that we talked about before, if I have a nonlinear system, and I were to do, for instance, LQR to stabilize the system in some region, you've done this on your problem set. Wasn't it annoying in the Acrobat to have to pick the region when you turn on your LQR controller? That's annoying, right? You don't have to do that anymore. You can call region of attraction. It'll tell you a region where it's guaranteed if I were to turn on the AR controller now, it'll work, and you can use that as your detector to flip it in. Okay? So there's lots of different ways you can put these together and make it work. And we'll have more examples and more complicated situations later. Also, I should say, Ani and Michael, your TAs, are two of the very best people in the world to be asked. If you have any questions about this, they're the experts. So you should absolutely ask them and use that resource if you're interested in this kind of stuff. See you next time.